In a previous video, we looked at refractive lenses and mirrors, which are essential for light concentration. In this video, we will look at other aspects of a concentrated PV system. You will learn about single and dual axis tracking systems, which are integrated into different types of concentrated PV systems. We will discuss the light concentration of CPV systems with mirrors and lenses and the different cooling mechanisms each uses. Concentrated photovoltaic systems consist of two principal elements, namely the optical collector and the receiver, which is the solar cell. The collector that concentrates the light can be a mirror, a lens, or a combination of both. Depending on the design of the collector, the system can be classified as either a linear concentrator or a point focus system. As discussed in a previous video, the collectors can only effectively concentrate direct light and are not effective at concentrating diffuse light. A CPV system therefore requires a tracking system to follow the sun's path through the sky during the day. Line focus reflective troughs generally use single axis tracking, where the collector can only rotate along the focus line. On the other hand, point focus optics usually require two axis tracking system, varying both the azimuth and the tilt angle of the panel in order to more accurately follow the sun movement. Although two axis tracking systems are more complex than single axis systems, they can achieve a higher average light concentration, which means higher power output. The further you move away from the equator, the more important the second axis becomes. This is because closer to the poles, the sun's path will vary more significantly throughout the year. This will be discussed in much more detail in the third course of our solar energy program. Due to high optical aberrations when the sun rays are not normal to the surface, Fresnel lenses are generally used in two-axis tracking systems. Tracking systems are only used for high concentration PV, with a light concentration of over 200 times the one sun illumination level of 1 kilowatts per square meter. Note that mirrors can also be used in dual axis point focus system, as shown in this picture. The light concentration can even be much higher. When lenses are used, the light concentration, capital C, is usually between 300 and 800 suns. For systems using mirrors to concentrate the light, the concentration can even go up to 1500 suns. You can imagine that under such intense levels of light concentration, the solar cells will heat up significantly. Special cooling mechanisms are therefore in place to prevent the solar cell from being damaged. Systems with lenses often use a passive cooling method. A large plate is connected to the backside of the solar cells. This plate, often copper, has a high thermal conductivity so that heat from the solar cell can be conducted to the plate. The large surface area of the plate means that the heat can easily be dissipated into the surrounding air. For mirrors, such a large conducting plate cannot be integrated, since it would block a large fraction of the incident light. Therefore, an active cooling system is used. For example, a continuous flow of water along the backside of the cell can be used to actively cool the solar cell. Some advanced systems use the heat produced by the solar cells in a CPV solar thermal hybrid system. Now in summary, in this video we discussed linear concentrators that use the single axis tracking and point concentrator systems that generally use dual axis tracking. We showed that depending on the type of optical collectors, either active or passive cooling is used to prevent the solar cell from being damaged. In the next video we will look into the effect of light concentration on the performance of solar cells.